ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, welcome to lecture number 26 in mechanical measurements. In the last lecture, we were actually discussing about the measurement of vacuum pressures below the atmospheric pressure. We considered one simple case of measurement using a McLeod gauge, which is some kind of a mechanical contrivance, because it uses the manometric liquid as a compressing fluid, which is going to compress the air or whatever residual gas in the vacuum system to a pressure higher than the pressure early at the beginning, so that the change in the volume is related to the pressure, and we also solved a problem based on this McLeod gauge. So, today what I will do is to continue with the measurement of vacuum. We are going to look at the measurement of higher than what we did last time, high vacuum. The three gauges I am going to talk about are the Parana gauge, the ion gauge and the Alphatron gauge. These are the three gauges I am going to quickly go through. Then I will change the topic to that of measurement of velocity, which is also a very important activity in most laboratory practice. The reason why I take measurement of velocity soon after the measurement of pressure is that many cases the velocity signal or the velocity information is converted to a pressure information. So, it is appropriate to take up the measurement of velocity soon after we have done the measurement of pressure, and that is the reason why we do that. Let us look at the measurement of high vacuum. So, the Parana gauge, the principle is very simple. If you have a electrically heated element, the amount of heat that can be transferred from the heated element is related to the speed with which this can be carried by the surrounding fluid, and as the surrounding fluid pressure reduces, the amount of heat it can take away also reduces, and therefore, if you heat an element, it will in the presence of the background pressure, which may be vacuum pressure. If the vacuum, as the pressure reduces, the temperature of the element will increase. If we keep heating with the same amount of current, the temperature is going to increase. So, as you remember, when we were talking about thermometry, if you have a resistance element and we heat it or we pass a current through that, its temperature is going to increase, and as the temperature increases, the resistance of the element also changes. So, the change in the resistance is what is going to be measured, just as we did in thermometry, but here instead of relating the change in the temperature or the change in the resistance as a consequence of the change in temperature to the temperature, we are going to link it with the pressure in the background. So, it is essentially the RTD principle, but it is called the Parana gauge, and what we have here is the schematic of a Parana gauge. What we have are two elements. This is resistive element 1, this is the resistive element 2. The first one, which is shown in green color here, is in communication with the vacuum whose pressure I want to measure, and the second one is a compensating resistance which is going to be put inside a sealed vessel, evacuated and sealed, evacuated to a very low pressure, very high vacuum or very low pressure. Therefore, the evacuated and sealed gauge, which is shown here, will not respond to the change in pressure, because there is no change in pressure here. It is going to respond to change in the ambient temperature. So, if the ambient temperature changes, it is going to respond, and the ambient temperature is also going to respond, change the resistance of this. Therefore, that is going to compensate. So, when we say Parana gauge with compensation for ambient temperature variation, what I mean is that I am going to use this evacuated and sealed gauge as a compensating element, whose change in resistance because of the ambient temperature is going to compensate for the change in resistance of the gauge here. So, let us see how it is going to operate. I have a source of power, and the source of power is going to set a current through the gauge here and also the gauge. It is also going to send a current through R1, R2 and R3. R3 is a variable resistor. So, what I do is I treat R1, this gauge, R3, the compensating gauge, as a Wheatstone bridge. You can see that this forms one arm of the bridge, and this forms the other arm of the bridge, and the other side is connected to the negative of the battery, and the battery is going to provide a source of power. It is going to heat the resistance here and also the resistance here by sending a current through the element. Suppose we adjust the, for example, here you can see what is going to happen. I am going to have, when the R1, this resistance, this resistance, this resistance can be balanced, and then when the temperature of this changes with respect to the temperature of this, and therefore, the resistance is going to change. So, I am going to keep a constant current through this circuit here, or I am going to a constant voltage is supplied here. The resistance of this element is going to change because of the pressure to which it is exposed. Therefore, the bridge is going to go out of balance, and a certain imbalance current will flow here, and this imbalance current will directly be proportional to the vacuum pressure. So, in the case of Parana gauge, we essentially have two RTDs, or resistance temperature detectors, like structures here. These two are heaters. The temperature of the wires change in response to the vacuum pressure, and therefore, the resistance changes. Because of that, the Wheatstone bridge circuit is going to go out of balance, and the imbalance is measured by the current which is shown here. And the range of this instrument is from 1 micrometer pressure, that is 10 to the power of -6 millimeters of mercury, to 1 millimeter of mercury, 1 torr a gauge, or 0.1 to 100 pascals. This is the range of this particular instrument. Usually, the Parana gauge is used with the rough vacuum pump. When the rough vacuum pump reduces the pressure of the vacuum space to a value lower than the atmospheric pressure, and it reaches the value somewhere in this vicinity. Up to this, we can use the, from 100 pascals to about 0.1 pascal, we can use the Parana gauge. If the vacuum pressure is even lower, that is higher vacuum, lower pressure, I will have to use a different type of gauge. And for that, I use what is called an ionization gauge. The principle of the ionization gauge I will explain first, and we will see how it operates. So, essentially what the ion gauge has, ionization gauge or the ion gauge has, it consists of an evacuated glass envelope, within which we have a plate, 3 electrodes essentially. One is the plate, second one is a grid in the form of a perforated sheet, or it may be in the form of a cylinder. So, I have a grid, and then I have a hot filament, which is the cathode. Okay. This filament is indirectly heated, so that it is at a high temperature. Actually, it is going to glow like in the filament in a bulb, and therefore, it is going to be quite hot. There is one type of ion gauge where the temperature of the filament is high, and it is the hot cathode which is going to give out electrons. The electrons are going to be released by the hot method by thermionic emission. And let us see what happens to these electrons. The electrons are going to move through from the filament to grid, because I have got a certain potential difference between the filament and the grid. You can see that I have connected a battery here. Therefore, the grid is positive with respect to the filament or the cathode. The electrons which are ejected from the filament are going to be accelerated towards the grid, because it is at a potential higher than the potential of the filament. So, the electrons are going to move in the direction from the filament to the grid, and now remember that this is connected to the vacuum system whose pressure I want to measure. Therefore, there are some residual molecules which are present inside this envelope here. So, the electrons which are moving with high velocity because of the accelerating potential are going to hit or collide with the gas molecules, the gas molecules which are still present within this space. Of course, the number of gas molecules present will be reducing as the pressure becomes smaller and smaller. Okay. So, the gas molecules are going to be hit by the electrons, and the gas molecules are going to become ionized. So, these ions are going to be positive ions, and therefore, if I have a plate which is, you can see here, it is connected to a battery here, such that the plate is negative with respect to the both the grid as well as the filament. Therefore, the positive ions are going to be accelerated towards the plate, and the ions are going to be neutralized. Ions are going to be neutralized on the plate, and therefore, the ions will go through this circuit and give a current due to the ions, which I call as the plate current IP. So, the plate current is because of the ions which are going to go and hit the plate and go through this circuit. You also remember that we talked about the electrons to start with. These electrons are going to accelerate, hit the molecules, ionize them, and continue towards the grid, and the grid is at a positive potential with respect to this. Therefore, the grid it will pass through this circuit and provide a grid current. So, there are two currents here. The first current due to electrons is through the grid circuit, and this is called the grid current Ig. The second one is the current through the plate circuit, which is called the IP or the plate current, and there are two currents, one due to the electrons and the other due to ions. Now, let us just look at what is the relative magnitudes of this. As the number of molecules are going to dwindle, are going to come down, the plate current is going to reduce, because the number of gas molecules which are there to be ionized is becoming smaller, and therefore, the plate current will become smaller and smaller as the vacuum becomes higher and higher. Therefore, the ratio of these two currents, the I plate current to the grid current, is the crucial thing which is going to tell us what is going to be the pressure. The range of this instrument is only 1 into 1 to 10 to the power of minus 5 micrometer gauge, or 0.01 to 10 to the power of minus 6 pascals. Very, very high vacuum or very, very low pressures we are talking about. Let us look at the relationship. The pressure inside the chamber, inside that glass envelope, is given by the ratio of the plate current to the grid current. You can see that as the vacuum pressure is becoming smaller and smaller, the plate current is going to become smaller and smaller, the gauge, the grid current is going to become relatively larger, and therefore, this ratio is becoming smaller and smaller. So, as the pressure inside the chamber becomes smaller and smaller, that means higher and higher vacuum, the pressure is actually proportional to the ratio of the plate current to the grid current, with a sensitivity factor 1 over S, and this is the S is called the sensitivity factor. The vacuum pressure, as you can see here, is a linear function of the ratio of plate current to the grid current. Therefore, you have to measure the plate current, measure the grid current, take the ratio. Of course, this all can be done electronically, multiply by 1 over S, and what you see in the meter will indicate directly the pressure in so many micrometers of mercury. The gauge constant S is also in fact called the ion gauge sensitivity, and a typical value of that is 200 divided by core per unit pressure. The unit of pressure used is torr, 200 per torr, or it will be given in terms of 2.67 per kilopascals. The gauge has a range from 0.1 to 10 to the power of 9 pascal. This is the range of the pressures which it can measure. So, to just summarize, the plate current becomes smaller and smaller as the pressure becomes smaller and smaller. The gauge pressure remains more or less the same, and therefore, the pressure is directly proportional to the plate current and of course, inversely proportional to the gauge current, the grid current, and the grid current will also vary to some extent, and the plate current variation is actually going to mirror the pressure inside the envelope. Usually, the envelope is made of glass and the filament works operates around 3000 degrees, 2500 degrees, like the electric bulb, and usually it is connected to the vacuum chamber either from outside or it is allowed to hang inside the vacuum chamber. If it is allowed to hang inside the vacuum chamber, it also provides illumination. So, you can actually use it to see what is happening inside the vacuum chamber. So, there is an advantage of putting it inside the vacuum chamber, allow it to hang inside there, and it is going to measure the pressure, at the same time also provide illumination within the chamber itself. And usually the way we operate the ion gauge is, the first you turn on the vacuum pump, the rotary vacuum pump, which will reduce the pressure to a sufficiently low value, so that we can turn on the high vacuum part, either the diffusion pump or any other pump which is going to be used for creating higher vacuum, that will be operated or that will be started only after the pressure has reduced sufficiently. During the first part, when the rough vacuum pump is on, you can use the Parana gauge, which will be attached to the vacuum system, and once the Parana, it will show the minimum value after some time. After the pressure has come down to sufficiently low value, the Parana gauge will indicate almost 0. That means that it cannot indicate anything sensitive, the sensitivity is very poor there. So, at that time the ion gauge will take over and the ion gauge will give you the pressure. So, this is how it is going to operate. The ionization gauge can also be replaced by what is called a penning gauge. The difference between the ion gauge and the penning gauge is the working principle is the same. Only thing is, in the case of the penning gauge, the filament is not hot. However, what we do is we have a very large potential difference, so that the ionization of the gas, residual gas takes place because of the high electric field near the cathode. So, when you have a very high electric field, that ionizes the gas instead of the hot cathode, which is going to evolve electrons. So, the way the ionization is going to take place is different in the penning gauge. Penning is the name of the gauge, is different from this. So, I am not going to discuss it further, just to highlight that you can also have a cold cathode gauge, which is also called the penning gauge. The third one, which I mentioned, is called the Alphatron gauge. Again, the principle is similar to the previous gauges. The principle is that you must somehow ionize the gas. If you ionize the gas or the residual gas which is present inside the gauge or in the vacuum chamber, it will create a current. This is the principle, and the current will be smaller the pressure. This is as simple as that. So, the way we are going to create the ions is different in the case of the Alphatron. In the Alphatron, what we have is a radioactive source, and it ejects radioactive, the alpha particles. For example, I can have a piece of radium here, it gives out alpha particles. These alpha particles are going to bombard at the gas molecules, and the gas get ionized. So, very simple, straightforward, no high temperature involved, no current involved here. The radium source is put inside the gauge, and the gauge is of course connected to the vacuum chamber at the side here. The radioactive source is kept here, and we have a needle which is the ion collector. The needle is simply a needle which is introduced like this. It is insulated from the body, and the body itself is the negative electrode. So, outside I have got simply a resistor and a potential difference by a battery, and what happens is that the ions are going to create a current, and the current is going to pass through this, and there is a certain potential difference out across the resistance, which is going to mirror the pressure inside. The advantage of the Alphatron gauge is that it can work from the highest pressure to the lowest pressure without any problem, because there is no filament, no problem with any of those structures. It will work even at the atmospheric pressure. That is why I have said here range is 0.001 to 1000 torr, 0.001 millimeters of mercury to 1000 torr, or 0.1 to 10 to the power of 5 pascals. So, the advantage of the Alphatron gauge is the Alphatron is actually a trade name of the gauge made by the Alphatron company. So, the advantage of this is that it can go from atmospheric pressure all the way to the vacuum pressure. So, there is no need to worry about the safety of the gauge, it is simply the radioactive piece of material which is going to be present there. So, basically what we have done is to quickly go through the different types of gauges which are used for the measurement of high vacuum, and I think this is sufficient for the sufficient exposure for the beginner. If one wants to learn more, one can always go to higher books which specialize on high vacuum engineering. That is what I would recommend the student to do if he is really keen or interested. And usually mechanical engineers do not come across high vacuums in their day to day activities. It is the chemists and physicists who usually work with high vacuum, and they will of course need to know more about the vacuum, how to create it, how to measure it, and so on. So, with this we will formally complete our discussion on pressure measurement. We have considered, just to recapitulate what we have done in the last few classes, we have considered different types of pressure measuring instruments starting from manometer. We also considered different types of gauges, and then we also discussed the transient response of these gauges due to process connections and so on, and then we have looked at the vacuum measurement of vacuum pressures or very high, very low pressures, and that has more or less completed the discussion on pressure measurement. The next quantity I am going to look at is the measurement of velocity. Of course, velocity measurement may involve the velocity of particles, it can involve the velocity of liquids, it may also involve the velocity of gases. We will, for our purpose, we will look at only the measurement of velocity of either liquids or gases. The velocities of particles and so on is not of much importance to us, and therefore we will not be looking at it. We are going to concentrate on the measurement of velocity of either liquids or gases, and therefore we can say fluid velocity is the quantity which is measured. Corresponding to the fluid velocity, there is also another thing which we may be interested in, the measurement of flow rate. Suppose a flow is taking place within a duct or a tube, we may be interested in measuring the velocity at every point within that fluid flow domain. We may also be interested in finding out how much fluid is crossing any cross section of the tube in unit time. So, the measurement of flow rate is a sequel to the measurement of velocity. So, the measurement of flow rate I am going to take a look at as in a different module, because I am going to look at it as a measurement of a quantity which is somewhat not like, if you remember what we said to start with, we were looking at the pressure, temperature and the velocity. These are all variable with respect to location within the domain, and therefore we are talking about functions of space, and therefore these are field quantities. So, the velocity is now looked upon as a field quantity, and therefore I am going to look at the field quantity measurement in this particular, in the next 1 or 2 lectures, and then we will come to the flow rate at a later stage. What are the different ways of measuring the velocity of a fluid? So, I am just giving here a few different types of measurement practices. One is to use velocity measurement, use a Pitot tube. This is a Pitot tube or a Pitot static tube. Either a Pitot tube or a Pitot static tube is going to help in determining the velocity at a point, and therefore I can use a Pitot tube or a Pitot static tube to map the velocity variation within a flow domain. Therefore, that is the advantage of the Pitot tube or Pitot static tube. The operating principle of the Pitot tube or the Pitot static tube is the fluid mechanics principles are involved, and therefore we will be digressing a little bit and then learning about these principles, so that we can use the Pitot tube or the Pitot static tube for the measurement of velocity. The second method which you can think of is, again we are coming back again and again to the thermal type of measurement. A hot wire anemometer is simply nothing but a resistance whose temperature is going to respond to the velocity of the fluid which is flowing past that. Just a little while ago we talked about a Parana gauge. The Parana gauge, the temperature of the wire or the element, heated element, depends on the ambient pressure. So, the pressure reduces, the temperature is going to increase because we are heating it with a certain amount of we are putting a certain amount of heat into it by sending a current, and this is going to increase, the temperature is going to increase as the pressure decreases. In that case, in the case of Parana gauge, we are looking at the pressure as a function of the temperature of the element, whereas here in the case of a thermal velocity measurement technique, which is known as the hot wire anemometer, I am going to send a current through an element and keep its either keep the temperature of that element constant or allow it to vary. There are two different ways of working with it. The basic principle is that the amount of heat that can be dissipated from the element depends on the flow velocity. If the flow velocity increases, we know from our heat transfer studies that the heat transfer coefficient is going to increase because of convection, and if the heat transfer coefficient increases, for a given temperature it can dissipate more heat, or for a given, if you put a given amount of heat, the temperature of the element is going to become smaller. If the temperature reduces, the resistance of the element will change, and it will again, it can be measured as a change in resistance can be measured as a change in the temperature. Change in the temperature can be ascribed to the velocity of the fluid. So, the hot wire anemometer is a thermal effect meter. Thermal effect or flow on a hot wire element is what is used in the hot wire anemometer. The third one is called the laser Doppler velocimeter. In this case, of course, the Doppler effect is going to be the main method, and we will of course discuss it more fully later. The Doppler effect takes place when the laser light is scattered from particles which may be present naturally in the flow. When the flow contains some particles, if we assume that the particles are moving along with the flow at the same velocity, the laser beam is going to strike on the particles, and therefore, they are going to be scattered, and because of the velocity of the laser, the particles, the light which is scattered is going to have a different frequency. So, we are going to measure the Doppler shift in the frequency, and we are going to relate the Doppler shift to the velocity of the particle, and the velocity of the particle is going to be related to the velocity of the fluid which is carrying the particles. If we assume that the particles are very small and they do not have any slip with respect to the flow of the fluid, that means that the fluid velocity and the particle velocity are the same, then we can measure by using the Doppler shift, we can measure the velocity of the particles and say that it is the same as the velocity of the fluid. The advantage of the laser Doppler velocimeter is that it is a non-intrusive method, while the two methods number 1 and 2, the Pitot tube, Pitot tube, as well as the hot wire anemometer are intrusive in nature. That means that I am going to introduce some probe into the flow field, and whatever may be the size of the flow of the probe, however small it is going to certainly affect the flow field. This is from fluid mechanics. We learn that there will be some kind of an effect of the probe on the flow field, it will disturb the flow field. However, the laser Doppler anemometer, in the case of laser Doppler, the laser beam itself is not going to disturb significantly, and therefore, we can say that the laser Doppler velocimeter is almost like a non-intrusive method. So, the three methods I have labeled here. The first two are actually probe techniques, because we are going to introduce something into the flow, and the third one is a non-intrusive technique, where only a light beam or two beams of light are going to intercept the molecules of the fluid which is flowing. The third important point is that the laser Doppler velocimeter, the control volume over which this measurement is done is very, very small. That means that it is almost like making point measurement. In the case of Pitot tube, pitostatic tube, as well as the hot wire anemometer, there is a physical size to the probe, and therefore, the velocity is averaged over this physical size, which is not insignificant. It is going to be finite, whereas in the case of laser Doppler instrument, the size of this control volume is so small that it is almost like measuring the flow or the velocity at a point. That is the main advantage. And therefore, if I use a laser Doppler instrument and measure the velocities at various points within the flow, I can get a very good map of the velocity field, whereas the other two are going to give somewhat less accurate picture. The laser Doppler is going to give you a very accurate picture of the velocity field. So, let us look at the other types. The first type is what I am going to look at first, the Pitot tube and the Pitot tube, and then of course, we will come back to the other ones as we go along. So, the first thing we are going to look at is the velocity measurement using Pitot tube, and let us look at two things. One is we will look at how the Pitot tube is arranged, what is the guiding principle of operation, and then we will of course, will take up an example later on. So, I have shown here a tube which is carrying a fluid flowing at a velocity v, and my intention is to measure the velocity of the fluid. Of course, in this case I have shown the Pitot tube. Pitot tube is nothing but a small diameter tube with a hole in the front here at the tip. There is a hole at the tip, and the hole communicates through this to a U-tube manometer, and the other end of the tube is connected to what is called a static tap on the periphery of the tube. So, there are two connections to the Pitot tube. One is the connection here to the at the side of the tube, that is called the static tap. We will describe why it is called static tap in a little while from now. We also have a hole in the tube which is going to be facing the flow. It is going to face the flow, and I have got a manometric liquid here, and let us see what is going to happen. The flow is coming from this side, it is going to come, and it is going to come to rest at the front stagnation point of the Pitot tube, which coincides with the hole in the front of the tube. The streamlines are going to divide and go from the sides, and therefore, the pressure at the point shown here, at this point, is going to be the stagnation pressure, whereas the pressure measured by the static tap, which is connected to the side of the tube, is going to be the static pressure. We will describe this terminology in a little while from now. The static pressure and the stagnation pressure, the difference is actually the dynamic head, or the head due to the velocity of the liquid or the fluid which is moving in the tube. So, the difference here, Hm, is the manometric height which is measured here, is convertible to a delta p, and delta p, which is measured by this head Hm, is nothing but the difference in pressure between the stagnation point and the static pressure at the wall. So, the head Hm, which is measured here, you see now what we are doing, we are converting the velocity which is going to give rise to an increased pressure at the stagnation point. This increase in pressure is because V is going to be brought to 0. So, this process is called the stagnation process. The velocity which is V is going to become 0 at the stagnation point here, and therefore, along the streamline, if you apply the Bernoulli principle, the pressure is going to continuously increase and become equal to the stagnation pressure at the stagnation point, and the velocity is going to be 0 at that particular point. Here the pressure is going to be the static pressure, and therefore, the pressure difference between here and here, which is measured by the manometric head Hm, is related to the pressure difference, which is equal to, which is related to the dynamic head. Dynamic head is in terms of V squared by 2, V squared by 2. So, the kinetic head or the velocity head. Therefore, I can measure the velocity from the Hm which is measured. So, this is a Pitot tube with a static tap on the wall of the tube, and the stagnation being shown by the hole which is going to be connected to this. This tube is going to give you the stagnation pressure and static pressure here. In the case of phytostatic tube, what we do is we combine the two on the same probe. We combine the static tap or the static hole as well as the stagnation hole on the same probe. In the case of the phytostatic tube, in the case of Pitot tube is separate, stagnation hole is different, the static hole is on the periphery of the tube. In the case of phytostatic tube, both the stagnation as well as the static holes are present in the probe itself. Let us look at the way it is going to be arranged. I have a tube as in the previous case, which is going to face the flow. The velocity is here, the flow is taking place here. The probe consists of an inner tube. You can follow the inner tube here, as I am showing, that is the inner tube. So, inner tube, and there is an outer annulus, which is connected to the other side of the manometer. So, the outer annulus is connected to the other side of the manometer, and you can see here there are holes on the periphery of the outer tube, somewhere downstream of the stagnation point. The stagnation point is here, the static holes are somewhat in the downstream of that hole, and I will mention exactly where it is going to be located in the next slide. So, the static holes are on the annulus portion, the stagnation hole is in the front, and the pressure difference is between the stagnation point here and the static pressure through the static holes. And in fact, what we normally do is on the periphery of the outer tube, there will be small holes uniformly spaced across the along the periphery of that tube. We have small holes, so it actually averages the pressure around the tube at this particular section. Again, the static pressure, stagnation pressure is acting on this side, the static pressure is acting on this side. The difference in head between the two sides is actually going to be dynamic head, and the dynamic head is going to be related to the velocity, and the velocity is therefore measured by measuring this head here. So, let us look at the details of how the phytostatic tube is actually made. I have made a slightly larger sketch. This is the inner tube, which is connected to this portion here, and the velocity is going to be v here, and this is going to come to stagnation at this particular point. The static holes, about 4 to 8 1 millimeter diameter holes on the periphery, are going to be at a downstream location greater than 4D, at least it should be greater than 4 diameters, where diameter is the diameter of the probe. Diameter of the probe can be about 7 to 8 millimeters. So, you see this is about 8 millimeters, 8 millimeters is about third of an inch, and the location is 4 times that diameter, more than 4 times. Typically 8 diameters, 8 into 8 millimeters will give about 60 millimeters from here to here. And between these holes and the place where this is going to be bent, the tube is bending here, I must have 8 diameters. So, the length from here to here is roughly equal to 16 diameters. So, if you make the phytostatic tube smaller in diameter, this will become smaller. So, the length from here to here is dependent on the diameter of the probe itself. We can make probes as small as 2 to 3 millimeters in diameter also. Okay? We can make very small one, and the curvature here in the bending in this portion should be something like 3 times the diameter, the radius of curvature of the mean line. I am talking about the tube mean axis of this one should be about 3 diameters. So, the phytostatic tube, the reason why we do these things will become clear once we look at the theoretical framework based, on which the whole thing is based. So, with this background, let us look at the Pitot tube as a means of velocity measurement. Let us look at the basic fundamental ideas about it, what are the principles involved, and let us look at what is going to be the relationship between the velocity and the pressure head we are going to measure using the manometer, which is an integral part of the pitot tube or the Pitot tube. So, the pitot tube or the Pitot tube I can represent by a bluff body like this. This is a body, this is a cross section is circular like this, and it is facing the flow. Flow is coming like this, coming like that. And what will happen to the streamlines is that the streamline comes here, the streamlines, neighboring streamlines are going to go like that, go like that. Okay. And at this point we have what is called the stagnation point. So, I am going to apply the Bernoulli principle or Bernoulli theorem to a streamline. Of course, you will have learned this Bernoulli theorem in your fluid mechanics course. So, I will take a point very far away and I will take the point O here. This, let us call this as point A. Point A is far away. When I say far away, I can interpret the following way. Suppose this is the diameter, I can take it a few diameters away essentially. Okay. And I am going to apply the Bernoulli principle, which says that the total pressure or the stagnation pressure is a constant along a streamline. So, I will say P T is the stagnation pressure it is also called the total pressure, which is given by at the point A I am going to have the pressure equal to, let us say, P infinity, this corresponds to P infinity, and the velocity is u, let us say this is u, plus half rho infinity u squared. This is at the point A. And at O, again stagnation pressure equal to the pressure at O, because u equal to 0 at O, u equal to 0 at O. When u becomes 0 at that particular point, the pressure goes up because the total pressure remains constant. I am assuming ideal fluid flow, that means there is no friction and other things are ignored, because we will later see how to account for them. So, the total pressure or the stagnation pressure given by P infinity plus half rho infinity squared is the same as the pressure at the point O. So, let us look at the consequence of that. So, the HM is the pitostatic tube or Pitot tube reading using a manometric fluid of density rho m. We can see that the delta P which is measured, the pressure difference which is measured, will be given by rho m G into Hm, where rho m is the density of the manometric liquid. So, we have the manometric liquid with density equal to rho m. We know that the pressure difference, which is measured by either the Pitot tube with a static tap on the wall of the tube or Pitot static tube, both are going to give the same information. The advantage of Pitot static tube is that there is only one probe, you do not have to make a hole on the periphery of the tube, otherwise there is no difference really. The advantage is that you can just make one hole and introduce the Pitot static tube into the stream. So, rho m into G H m is equal to delta P m, and this must be equal to P total minus P infinity, because that is the pressure difference I am measuring. And from the expression for P t, we know that P t minus P infinity is nothing but P infinity plus half rho infinity u squared minus P infinity equal to half rho infinity u squared. Remember that rho infinity is the density of the flowing fluid, rho m is the manometric fluid density, rho infinity is the density of the fluid which is flowing in the tube. Okay. So, I can combine these two now and say that half rho infinity u squared is equal to rho m G H m. Okay. And therefore, I can solve for u, the velocity. So, you can see that the velocity u will come out to be, I can make a little space here. So, I will say u is equal to, therefore, u is equal to rho m 2 rho m G H m divided by rho infinity under the square root sign. So, the velocity of the fluid is equal to square root of 2 times the manometric density multiplied by the gravitational constant multiplied by the head which is measured by the manometer divided by the rho infinity. Now you see that we have converted the measure of velocity. You can see this is nothing but something like some constant k times square root of h m. The relationship u is equal to some constant. Constant is nothing but the square root of 2 into rho m g by rho infinity is the constant multiplied by the square root of h m. So, the instrument is nonlinear basically, because the velocity is proportional to square root of the head developed, okay, k root h m, and the velocity information has been converted to pressure information, and the manometer has further converted the pressure information to the head of the height of the column information. Therefore, I am measuring the velocity in terms of a manometric height, which is going to be the result of the Pitot static tube being used for the measurement of density, the measurement of the velocity. Let us look at a few more details. And what I have done is I have plotted a simple sketch here. This is just to understand what is the proportioning of the Pitot static tube. So, I have again indicated the Pitot static tube as a bluff body, and I am looking at the change in the flow around this body. The flow is coming with a velocity u, and because of the body it has to go around it. We are assuming that the flow is ideal flow without friction. The friction effect can be taken care of by a suitable factor a little later on, we will come to that. The diameter of the probe is d, and what I am doing is I am trying to find out what is the pressure relationship, pressure variation with respect to the location along the body. Okay. For that I plot the P indicated at any location x measured as shown here. Actually I am measuring x as a ratio of x to d. So, what I do is, this is what I have plotted is x by d. So, x by d equal to 1, 2, 3 etc. I am measuring the difference between the pressure at any particular point minus the static pressure divided by half rho infinity u square. This is the dynamic head or dynamic pressure. So, the pressure difference as the ratio of the dynamic pressure. And you remember at the stagnation point, this must be equal to this difference must be equal to half rho infinity square. Therefore, the value of this will be exactly equal to 1 at the x equal to 0 or x by d equal to 0. And let us see what happens as we move along this like I have shown by arrow. If I move along this, the velocity is going to change because it is now encountering a body, it has to adjust itself. So, the velocity is going to continuously change, and in this portion the velocity is increasing, and because the velocity is increasing, it is not decreasing, actually it is increasing. The pressure indicated minus V infinity by half rho infinity square is going to become smaller and smaller, and at some point it is going to become equal to 0. That means that indicated pressure equal to static pressure, and then it keeps going down because the velocity is now increasing beyond that, and therefore, it goes to a minimum somewhere here near about 0.8 or 0.9 d, and then start again increasing, the pressure starts increasing. And if you see here about x by d of roughly equal to 4, this difference has become 0, the pressure has become equal to the static pressure. That means, somewhere here if you measure the pressure by making a hole on the probe, if you measure the pressure, that will be nothing but the static pressure. Therefore, the requirement is that the x by d must be greater than 4, that is what I mentioned earlier, and normally we take the x by d as about a value of 8 to be on the better safer side. Another 1 or 2 small points we will discuss. The second point is, let us look at the flow around this body. Some ideas from fluid mechanics we require, and I will just give the gist of the argument. If we assume that the fluid flow is taking place at a sufficiently high Reynolds number, so Reynolds number Re, if it is more than about 300 based on the diameter of the probe, so Red will be nothing but u multiplied by d divided by nu, where u is the velocity, d is the diameter of the probe, and nu is the kinematic viscosity of the fluid which is flowing. If this is greater than 500, the boundary layer is very thin. So, there is a boundary layer is very thin, and the pressure loss or loss due to friction is also very small, and therefore, for values of Red greater than 300, the value, the formula which I gave earlier is more or less okay. So, the formula can be modified by introducing a coefficient. Why do we require the coefficient? If there is friction, there will be some pressure drop due to friction. Therefore, whatever pressure drop I am measuring, it contains also pressure drop, some amount of pressure drop due to friction effect. But when I am measuring, I do not know which portion is due to friction, which portion is due to the stagnation process. When I am stagnating, the velocity head is going to be added to the static head. Now, because there is a certain amount of friction, the amount of pressure difference consists also not only of the dynamic head, also of some amount of frictional head due to friction loss. Because I do not know what that is, what I will be interpreting is that the pressure difference Hm rho m into G Hm is nothing but u squared by 2, that is what we said, rho u squared by 2. No, it also contains a little bit of frictional effect. Therefore, I have to multiply the formula by a coefficient which we call as C. So, if I go back to the previous slide, I will multiply this by a factor C. This is C is something like 0.98 to 1, depending on the Reynolds number. If the Reynolds number is greater than 500, so RED greater than 500, C equal to 1. So, we can multiply by a small factor 0.98 to account for the effect of friction. And in fact, let me just discuss a little more about this friction portion. If you look at the flow around this body, if the boundary layer is very thin, the boundary layer theory tells us that the pressure across the boundary layer remains the same. That means that the pressure I am measuring is the same as the pressure in the main stream or the free stream here. Therefore, when I said the pressure has become equal to the static pressure, the meaning is very clear. From here to here, whatever pressure difference pressure changes I am showing here are also the change of the pressure along the boundary itself. If you were to put a static hole all along this periphery and measure the pressure locally, you will see that there is going to be just this value. Whatever we are getting here is nothing but the static pressure variation along the boundary. This comes from the boundary layer theory, assuming that the boundary layer is very thin, and that is satisfied once you have a Reynolds number based on the diameter greater than about 300, it is going to be thin, and therefore, it is more or less satisfied requirement. But in order to allow for this small effect of the friction, we can multiply by factor which I showed in the previous slide. I will introduce a factor C which is between 0.98 and 1 to account for the presence of friction. So, to just recapitulate what we have done, we have started looking at the measurement of velocity in a flow, and in fact, there are many more interesting points which we will have to talk about. For example, I never talked about the direction of the flow. So, if I go back to this figure here, I have conveniently put the probe such that it is exactly normal to the flow which is coming in this direction. The flow is coming directly onto it, right. Suppose I do not know the flow direction, this is the, let us assume that this is the flow direction. If I put the probe like this, will it also give you the proper value? If I put it like this, that is, if it is at an angle with respect to flow, what is going to happen? It is a very important thing, because in some situations we may not know the direction of the flow, and therefore, we have to be careful about how to align the Pitot tube to get the proper value. There are some probes which are specifically developed, so that a small amount of angular inaccuracy in the or small angle between the direction of flow and the direction of the axis of the probe is not going to be important. So, we will look at some of these features in the next lecture. Thank you.